And so we were in the middle of talking about just what is the logistic model, how to use it, and sort of what are the basic mechanics of it. And I really want to sort of get through this because I really want to wind up talking about the EVW model, which is something new, rather than sort of reviewing the logistic model, which is obviously super important because it's the basis for everything we're doing. And so we sort of left off just after this last time where really when we're considering a dichotomous outcome where we're trying to understand the probability of y equals 1 or versus 0, let's say, that there's sort of these two equivalent models that are really the same thing. There's this probability form of the logistic model, 1 over 1 plus e to the minus all this stuff, and where this stuff is sort of looks like a linear regression model. And then there really is this linearized form of it, which is the logit form, which is the log odds equals alpha plus beta 1, x1, and so forth. So these are the same thing, and we just use them slightly. We use them, you're always modeling both, and depending on what answers you're trying to get, you might prefer one format over the other. And then we sort of talked about, well, what does this look like in a real example? And here's the MRSA example again, which I know you saw last semester a little bit, and here we're seeing it again. We'll move on to other examples. And here was just one model that we could have chosen. There's many, for these variables of, we have four x variables, x1 through x4. This is one possible model that you could fit. And essentially it has a main effect, a single sort of effect, statistical variable in the statistical model with no interaction, nothing fancy going on, where we just consider these four variables as such. There's no interaction. And we said that for this sort of simple model, oh, this is my old version of the slides, not the one that we used last time where these actually had the numbers in here. But for this simple model, we plugged in, if we had these values of previous hospitalization 1, age 35, sex 1, PAMU 1, we would plug it in this model here and we can get sort of probabilities out of this model. And if we wanted to know an odds ratio, we said that the odds ratio for any given item in this model, if we want to know the odds ratio for having MRSA comparing previous hospitalization yes versus no, it would just be e to the beta associated with that variable. And that would go for any of them. If you want to know about sex, and you said I want to compare sex 1 versus 0, you would do e to the beta 3. And this is sort of a very quick and easy thing, and it gets more complicated the more complicated your model gets. And so that's sort of where we left off last time. And the reason, the reason that this sort of works out the way it does is sort of on this slide here. Why is it e to the beta? Well, if we said that the log odds format was this sort of linear alpha plus beta 1 and so forth, and the odds version is e to that, right? And this is the odds when previous hospitalization equals 1 or yes, and that's essentially this e to the expression, but we put a 1 in here because we know that previous hospitalization equals 1. And when we compare that, when we say, well, what's the odds when previous hospitalization is no, it's the same exact thing but with a 0 here for the x variable associated with previous hospitalization. And if you said, let's hold everything else constant, I don't care what your value of sex, age, PMU, I just want it to be the same between people who are previous hospitalized, yes versus no, well, you just take the ratio and say, okay, I'm going to take the ratio of these two expressions. And it turns out, luckily, and a lot of stuff starts to cancel. So another way to write this big old fraction is as a big old difference between the numerator information here in the numerator, in the first part of the exponent here, so e to the alpha plus beta 1, that's previous hospitalization equals yes, all of this minus the exponent of the other fraction, the denominator there. So this, by the rules of sort of how we work with exponentials, you can sort of take this subtraction. And what happens is everything cancels except for beta 1. And that's why it was e to the beta 1. All these other things cancel because it's alpha minus alpha. Beta 1 minus, there's sort of no equivalent, but beta 2 times age minus beta 2 times age. Everything sort of cancels out because of this minus. And then lo and behold, it's e to the beta 1. And that's why it works out so nicely. And remember last time I was talking about how like regression is just another form of doing the twin study and all these babies and all of that. The reason that this is equivalent to that is we're sort of balancing two groups. We're sort of pretending that the numerator group is exactly the same in terms of their sex, their PAMU, and as the denominator sort of comparison. We don't care what, we're not putting specific values in because no matter what specific values you put in, it would always cancel if they were the same. And sort of it's this idea we're sort of artificially balancing a numerator group and a denominator group, those who are previous hospitalized versus not, by pretending that all their values are the same as between the two groups. And then everything cancels if they have the same value of sex, if they have the same value of age. And so this is where we're sort of balancing the confounders. We're holding all else equal when we divide through and cancel stuff out. And so here, like we just said, this is the model. So this was the model. This was the logit form of the model. And here was sort of the odds ratio expression for previous hospitalization. And here we have a hat over it that sort of means the estimated odds ratio, not just in theory what it is, but from the data, what is the odds ratio? What would SAS tell us? And that is sort of what we have below here. So when we put a hat over something, that means it's its estimate. This is sort of the theoretical algebraic version, and then we actually have numbers from an actual data set. We put a hat over it to say the estimated odds ratio. And so here, one of the first things that Proc Logistic is going to give you as part of it, the answers that it spits out for your data set and for your particular model, is it gives you this thing of analysis of maximum likelihood estimates. And here is an estimate that says pre-hosp, and that is the estimate. This row represents the beta 1 associated, the beta term associated with that variable. And here we see it's 1.49. And so if we just exponentiate that, we get an odds ratio estimate, which conveniently you get a table called odds ratio estimates. But this is not always the right answer that you seek. And so as you get interaction terms and more complex sort of representations of things in the model, this is not going to be right. Okay, this is a handy this is like just going to your calculator and going e to this column. That's all it is. It's just saving you the step. And so anything more nuanced is going to involve the contrast or estimate statements that we'll talk about. So this is, but in a simple sort of no interaction model, this is what you get. And this shouldn't be surprising. So compare this 4.4, sort of the odds ratio now adjusted for all this other stuff in the model for age, sex, and PAMU. It's similar, but not exactly the same as this answer that you would get out of the stratified analysis. And so does anyone know why they're not the same answer? Guess. They're similar, but not the same. So this is one of those, this is sort of one of the issues of stratified analysis that we talked about before. I'm not sure if it's the issue, but just one of the things to know about stratified analysis is that this has no interaction in it. This is just sort of a simple model. We put every variable by itself in, there's sort of, we call them main effects models, just the variable by itself. And this analysis is actually doing considering all of the nuanced interactions, because you stratified into 8 tables and everything's sort of adjusting for everything in 2-way interactions and 3-way interactions. This is the equivalent essentially of fitting a model with up to 3-way interaction in it. It's sort of why, that's sort of the reason that this is sort of super duper stratifying the data. It's sort of overkill, possibly. It's possibly overkill. There may not be interaction, but this model, this analytic approach to stratified analysis is sort of ready to handle any interaction. You've made 8 tables. You could detect all sorts of interaction in theory. Maybe that was overkill. Maybe you didn't have to do that. And it turns out this logistic model, it doesn't split the data so many ways and sort of overuse the data. It gives you almost the same answer. So you might actually, at the end of the day, conclude that this is just as okay. But they're close. They're not the same. They're close. So again, if we did this, if you did this with no other adjustment for anything else, if you just fit this real simplistic model, alpha plus beta 1 previous hospitalization, then they're exactly the same, because there is no other stuff to adjust for. There's only one 2x2 table that sort of represent, if you did a stratified analysis analog of this, it's just the 2x2 table of previous hospitalization by MRSA. And so this is exactly the same as a 2x2 table analysis. And if you never want to do the AD over BC formula again, and you just want to do Proc Logistics forever, you can sort of Proc Logistic your way out of a 2x2 table now, if you want to. And so here you're going to get exactly the same answer, the same confidence interval. It's pretty much the same. And again, this is because you didn't have that other, those other adjustment issues that we just talked about. And so here now we get the exact same answer. Okay, so that was that e to the beta business was convenient for the simple case of no interaction. But there's a more general form to handle any type of model, and it's exactly what we saw before. It's literally to get any odds ratio comparing anything to anything. It's just the ratio of the odds expressions for that we're interested in. That's why it's an odds ratio. So if the odds form of the model is e to the alpha plus beta 1, x1, and so forth, the basic idea here is in the numerator you sort of have the one group, and in the denominator you have the other group that forms the basis of your comparison. And so imagine you want to compare someone who's male and 35 versus female and 42. Then you literally could do that. You can make any custom comparison you want. We did this thing before where we held everything else equal. But you can make any comparison of any particular groups by plugging their x values into this formula, putting the estimates in for alpha, beta, and so forth from SAS, and then you compute the ratio. And then that is the odds ratio for the comparison you care about. And so this slide essentially is repeating all of what we just did to make it, to have everything cancel out so nicely. Things don't cancel out nicely. So we're using stars here to represent the numerator values and no star to be the denominator values. But this could be male versus female, 42 versus 35. These sort of different values, they only cancel out when the values are held the same, but they don't have to. And the idea here to see the common thread here is that you can even if things don't cancel, you can sort of rearrange and factor out things in such that the alpha is always minus alpha. There's nothing multiplying it. So it's always alpha minus alpha. The intercept always goes away. This is going to come back that's going to be important for conditional logistic regression and the case control studies. But everything else is just sort of beta 1 times x1 minus 1, beta 2, x2 minus 2. So you can sort of rearrange and factor it out so that it's the coefficient times the differences in some x's. Where the x's are the same, this whole thing becomes 0 and everything goes away. But in general, for any situation, it's just e to the sum, or literally all these different sums of all the betas times the differences in the x's. If you leave this course remembering one thing, because if you know this formula, you can apply it to any odds ratio in any situation. Please leave the course knowing more things. But if this was the one, this was like your Swiss Army knife, because you'll be able to sort of always figure out an odds ratio from this formula, because it's literally just the betas times the differences in the x's. And this is actually going to be very much the same for the hazard ratio and the risk rate and the rate ratio in Poisson in survival and Poisson regression. So this formula is going to keep coming back to us. And again, so we saw earlier when you have a dichotomous sort of binary 0-1 exposure variable, let's say if it's called x1 and everything else is the same and there's no interaction, this becomes e to the beta 1 in this case. So this is sort of the golden formula. And so this just sort of, I'm not going to belabor this. This essentially shows exactly how we did that with our example earlier, that we apply the 0 versus 1 comparison of previous hospitalization. You put it through the formula, and bam, you get back to e to the beta 1. So you don't need to see this again. I think an important point to appreciate is that the odds ratio is a multiplicative measure of effect. So in EPI 530, we talk about additive and multiplicative, and interaction is sort of evaluated on this multiplicative and additive scales. And that sort of relates to all this. And I'll show you what I mean here. So let's pretend we wanted to compare someone who had who's sex 1, which I think is male, maybe in the coding on the first slide, and then it's previous hospitalization 1, comparing to a non-hospitalized female, sex 0. Okay, so it's two things are varying, essentially, not just holding everything else constant. We're holding age and PAMU the same, but these two are going to vary. And what happens is all the other terms go away because they're sort of held constant. Age is the same and so forth. But here we have sort of two pairs of 1 minus 0 corresponding to previous hospitalization 1 versus 0, and then sex 1 versus 0. So this is now the odds ratio per our formula for sort of comparing these two sort of fictional people or groups of people. the males hospitalized versus the zeros for both. And what happens is we plug in this output from SAS, and this 11.2 sort of represents the odds ratio comparing people like this to people like this, sort of globally, controlling for age and PA mu. And again, because this is everything else sort of became 0 in our formula, and this is 1 minus 0 equals 1, and so it's just e to the beta 1 plus beta 3, and that's sort of this. Okay, why am I telling you all this? This is exactly the same result as if you did this. Multiply the odds ratio for previous hospitalization times the odds ratio for sex 1 versus 0. So this sort of joint comparison of one versus the other is actually the same as taking the individual odds ratios and multiplying them towards each other. I think this is just a cool thing to keep in mind, is that this is the odds ratios that you get out sort of, it's like always, imagine if, if it's, I don't say it's cancer risk. You see smoking, odds ratio 3, alcohol 2. So the joint intersection of those is 6 because it's 3 times 2. That each one of them sort of multiplicatively comes along and sort of whacks you or something, and each one gets their turn to increase your risk. One comes along and it 3-fold slaps you, and the other one 2-fold slaps you, and now you got a 6-fold slap. I don't know if this metaphor is working. But this idea is that each one comes along and increases your risk sort of independently of the other one that comes along and then increases your risk. That's sort of the idea, but not as violent, I'm sorry. But that's sort of the idea that there's sort of these independent processes, and you can do it this way where you vary both at a time, or you can sort of iteratively come through and multiply it. When you have interaction, this is not true. And when there's no interaction, this is the case, that they sort of independently, it's the opposite of no interaction in a sense, they sort of independently operate. When you have interaction, they don't independently operate, that they sort of work together in some way. So in the no interaction model, they're independently increasing the risk. And I think it's just sort of a cool thing to think about how your model's working for you. And this just sort of mathematically shows why that's the case, that it's sort of the continuous product through of all the different odds ratios. So with interaction, it gets a little more complicated. So with interaction, here's an example where we consider a different model. Let's say we have a model that's just these two, we have two sort of primary variables, previous hospitalization and age. Sex is on here and the PMU is in here. And so we have these sort of two primary variables, but now we have something previous hospitalization times age. So the idea here is that maybe there's some interaction where the effect of being hospitalized somehow changes across the lifespan or something. I don't know, the exposure changes across age groups or something, the effects of it. And so now this model is more complicated because it has the product of two other things. And now the comparison of previous hospitalization 1 versus 0 is not e to the beta. It's more complicated. And the reason is because if you apply our sort of golden rule formula of just sort of take all the differences in the x's and approach, well, what happens is not everything cancels so conveniently anymore. And the reason is, like, compare previous hospitalization 1 versus 0. Okay, so the numerator person, x star, is a 1. We don't care what their age is. We're going to sort of hold that fixed at some value. Let's say it's 50. Everyone's 50. But the thing is, you have another x variable. And this x variable is actually the product of the other two. And it's called 1 times age. And so you have a third x variable called 1 times age now. The other group, the comparison group, has a 0 for previous hospitalization age and then 0 times age. So what happens when you sort of run this through the formula? You get e to the beta 1 times 0. Okay, it's e to the beta 1. That's old news. We know that. Age minus age, that's this, sort of cancels out. But this thing does not, but look, this doesn't cancel out. So you have 1 times age minus 0 times age. So that's 0 goes away. And this becomes age in the parentheses. So age hangs out. This doesn't become 0. 1 times age minus 0 times age is age. Okay, so it sort of hangs out here. What do we do with that? What does that mean? It means that the odds ratio actually changes with different values of age, okay? And you're sort of like, oh no, that's really complicated. That's sort of annoying. I can't represent that well. That's irritating, right? Because age is continuous. But this is exactly what interaction is. Interaction is the idea that your or effect modification specifically is this idea that your exposure, your measure of effect, the measure of effect for your exposure changes because of the other variable that is being modified. And here, it turns out that the odds ratio is modified by the value of age. Depending on age, the machine You run it through your formula and you get a different answer, and that's exactly what effect modification is. The answer changes, and so we're going to get a different odds ratio depending on the value of age. And so here, if your age is 35, we're going to plug a 35, and this is the way you get the odds ratio for a 35-year-old. This is the odds ratio for a 60-year-old. So the measure of effect changes, the exposure measure of effect changes depending on this external variable, which is your age. So it's annoying formulaically that there's this, it's annoying formulaically that there's this something else, but it actually exactly flows from what we think effect modification is. Here's what is this? These are other betas. Here's a model that has sort of lots of interaction terms, this sort of previous hospitalization times each of these other ones. And this is to convince you that if you go through the formula again, what happens is all of the interaction pieces that are associated with previous hospitalization stick in the model. And now you've got an odds ratio that depends on sort of 3 other variables, age, sex, and PAMU. But this is, again, this is just to show that it's going to, everything, these sort of main effects for the age, sex, and PAMU cancel out, but the product terms stay in there because they don't cancel out. So I'm just going to skip over that, working that through in super detail. This is sort of that last one where you have all these things hanging out in the numerator, and depending on, you have to plug in the beta values from SAS here, from the table. Here's sort of the interaction term beta estimates. They sort of go in here. And you plug in different values. Here's 35-year-old, sex 1, PAMU 1, age 60, sex 1, PAM 0. And look, you get all these different odds ratios because you're sort of feeding your formula different values of the effect modifiers. These are the 3 pieces that are modified, that are multiplying times previous hospitalization. And lo and behold, you get different answers. So this group's at more risk than 35-year-old sex 1, PAMU 1 is at more risk than this group because they're or more risk in terms of the effect of previous hospitalization for them is higher. So their odds ratio for previous hospitalization is 8 versus 3.3 for this group. So you can have interactions where it's pulling things in all sorts of directions depending on all these other covariates. And so this can get really complicated. And with the modeling strategy stuff that we're going to do starting next week, we're going to sort of talk about sort of how do you navigate this complication with lots of interaction terms. And so there's actually sort of another formula which is a special case of the other formula that was sort of the generic how to find any odds ratio, which is that when you have interactions of a very specific type where the interactions are all sort of multiplying your exposure like we had before, then you can actually write the odds ratio as e to the beta 1 plus all of the betas for the interaction terms, essentially, times the effect modifiers. So this is essentially, we're going to talk about this a lot in the EVW model. The betas associated with the interaction term stay, and the other pieces that we previously had canceled in the other models to get e to the beta 1, they still cancel. But the interaction terms with the exposure stick around. That's the special case. This is the generic version of what we just saw here, where everything else canceled, and we have these interaction terms with age, for age, sex, and PAMU. Those hang out. And so that's sort of the idea for the odds ratios. So online on Blackboard, we have a slide set that goes, we don't really present it in the lecture, but it's something to check out. It sort of was in the lecture 1 area that was sort of odds ratios. It's called like something with odds ratios. Here it's odds ratios examples. And I would just take a look at this. I think our TAs might go over pieces of this in lab. And this is really sort of working through the same formula for the odds ratio, but just sort of exploring what happens under different scenarios. And we're going to refer, you're going to start seeing examples later that use some of these situations. So the basic one is one exposure that was binary. And so that's what we've seen, that's e to the beta. Then but things can get more complicated. You can have an exposure that's a continuous variable. So what if it's, some alcohol dose or something is the exposure, and then how do you sort of talk about odds ratios with a continuous sort of comparison? What happens when the exposure is categorized by more than 2 levels, right? In logistic regression, we're talking about 2 levels for the outcome, but who says the exposure has to be dichotomous, right? The exposure doesn't have to be at all. And so what if you have a 4-level exposure? What if it's city or whatever, who knows what it is? How do you deal with that? How do you deal with that? What do you do? Dummy variables. You do dummy variables, right? You set up these sort of pairwise comparisons. You make a reference group. It's sort of stuff we've all seen before. Like you have a multiple level, you have 4 levels of city, so you make 3 city dummy variables. And now you have 3 odds ratios to make all the city comparisons. They're all sort of variations of this e to the beta theme, and they're just sort of worked through one by one in this slide set. It would be really boring to watch me do this, to sort of say, now what if it's categorical? What if it's continuous? So we have this, I would just go through it. It's going to validate a lot of what you know already, but I would just check it out because it's going to be helpful. The last one, and then we have a sort of a lecture at the end of modeling strategy on this, is what happens when there's multiple exposure variables, and that's a little more complicated to think about, but it's all in there as well. So I'm going to take a jump here towards statistical inference, because getting an odds ratio is very nice. That's sort of the first thing. That's the point estimate. But ultimately, we wanted to do hypothesis testing and confidence intervals for the odds ratio. We don't want to just sort of stop at the odds ratio, because the question is, okay, so is it significant? Is it significantly different than 1, such that we think there's not, if 1 is sort of the odds are the same between the 2 groups, we want to see some departure from that to think there's something interesting going on. If is your odds ratio of 2 significantly different than 1? And then the confidence interval, which is, okay, well, how precise do you feel that your odds ratio is? And so is, if your odds ratio is 2, is 1.5 sort of a credible value that you think? What's sort of your statistical uncertainty around the odds ratio? And these are super duper linked, as I'm sure you've worked over in every course so far. Right, that the hypothesis test and the confidence interval are very, very related concepts. They sort of turn one on the other's head, right? So, because what happens if a confidence interval contains 1, right? Then you would fail to reject your hypothesis test, because you would say, oh, we can't rule out an odds ratio of 1, therefore we also would fail to reject the null hypothesis in a test of odds ratio equals 1. So these are very, very related. And we're just going to sort of talk through how we do this with logistic regression. And so it all has to do with this thing called maximum likelihood estimation that we're going to talk about. So the real question is, how does SAS come up with its estimates of those betas? Where does it come from? And then similarly, where does it come up with the variance or the standard error, which is the square root of that, of these pieces? And you need the variance or standard error for the betas in order to do the statistical inference sort of component. And there's this thing called least squares. Least squares is sort of asking rhetorically, should we use least squares? That's the method that we use for linear regression, where you sort of, remember like in the simple linear thing, you do have these points, and you minimize the distances of all the points to the line, and like the best line that sails right through that is the least squares method. It minimizes the distance from all points to the line. And so that's actually not the best methodology for logistic regression. Instead, we use something called maximum likelihood estimation. But just to take a retrospective, this is what we did in linear regression. This is what we used to do. And now we're going to sort of come up with the logistic regression versions of all this stuff. So we used to do this thing called a hypothesis test, right, or rather a single beta equals 0, right? And that's, a moment ago talked about 1. That was for the odds ratio, right? The null value for an odds ratio is 1, and sort of the null value for on the betas is 0. And by the way, what's e to the 0? 1. So that's e to the beta. The null value of e to the 0 is 1, and sort of it all perfectly works. But in linear regression, we were all hung up on about betas equaling 0, and we sort of defined 2 types of tests for that. One was the partial F test, that sort of compared the sums of squares, for the x you care about given the other ones over the full model. That had an F distribution. And then then we had this thing that was a t-test. Okay, that was the beta over the standard estimate of that beta. That was sort of a t-test that came out of linear regression. And so we're going to have versions of this. And then we had also this thing called, we wanted to test a set of betas equal 0. Like, what if these 3 betas are all equal to 0? In linear regression, that was called the multiple partial F test. And that was also an F test. And then we did this confidence interval thing, right, for the betas, which was beta hat plus or minus t a t-distribution parameter times the standard error of beta hat. This is going to be very, very similar in logistic regression. So we did all this before, and now there's sort of a logistic regression version of it all. And it all hinges on this thing called maximum likelihood estimation. And so the deal with maximum likelihood estimation is L is this quantity that represents the probability of observing your data. And we'll sort of see what exactly that means. It's a probability function that represents the probability of seeing your data. And we're going to say it's a function of the parameters we care about, alpha, beta 1, and so forth. And we're going to essentially take our data and solve a series of equations that solves for these alphas and betas and so forth. And we want it, the value, we want to find the system of solutions that maximizes this probability of the data called L. And that the computer is going to iteratively solve all this, okay? We're going to very lightly touch on this, and then Zach's worksheets sort of take this to the next step of understanding. And so I think, this is going to be sort of round one, and you can sort of take it further at home. And there's sort of two flavors of the maximum likelihood method. There's something called unconditional, which is the usual way, and then there's conditional. Did you guys do conditional at all in 534? Yes. For matched analysis? Yes. Okay, I think so, right? Yeah. I hope so. We're going to talk about it more on Thursday. There's this thing called the conditional version, and it's what you do when you have essentially really sparse, often you do when you have sparse outcome data and relative to how many X variables you have. So you've got a lot of X variables. So in a matched analysis, if you've got like 100 matched pairs, that would actually be 100 covariates. So that's a lot of X variables. And so the way to deal with that is something called conditional logistic regression. And you're essentially, it's good for pair matched or household data. I'm doing an analysis of sex in Zika transmitting households, and we're using conditional logistic regression because we have households. And so it's a really good thing when you have matched data. And so here's a really simple analysis, a simple analysis for the unconditional maximum likelihood. Suppose you have data on 100 subjects, and 75 of them have the outcome 1. Then, and it's a binary variable, 25 have 0. And then we say that this is sort of distributed, this is say binomial, not binary. That we know that there's the binomial distribution that would describe something like this, where you have a disease outcome and 75 people have it. We say that these data are distributed binomial. And so the binomial distribution, right, if you remember, it looks something like the total number of trials choose the number of successes times the probability of success to the number of remember this whole business? This is the formula for the binomial distribution. This describes this situation very specifically because I actually plugged in the 100 and the 75. This is the formula, this is the distribution that dictates the outcomes of studies like this, where you have 100 people and there's 75 have the event or not. Okay, so imagine if you didn't know what the probability of disease was. So I parachute you into a village, and your job is to sample 100 people and figure out what proportion of them have condition Y. And you do that, you take your blood or your surveys or whatever, and you come back and say 75 have Y. And you want to know, okay, well, what's the probability? Like, I want to make some inference about that. I want to know what the probability of Y is. What's your best guess at Y? And you would intuitively say 75%. Like, you would just say that because that's sort of, you're mathematically minded, and you would say, oh yeah, it must be, the most likely value is that the probability of getting the condition is 75%. Because 75 people had it. But that's actually a huge leap of faith, right? You actually have to that just because 75 have it doesn't, that you intuitively think that's the most likely outcome. And the reason it actually mathematically works out that way. If this thing is called the likelihood distribution, this is the probability distribution, but it's also the likelihood distribution for your data. And you saw if you maximize this function, which in calculus terms is you sort of set the derivative equal to 0, or the first derivative equal to 0, and find and solve for p, it turns out if you said, I want to take the derivative of this and set it to 0 and solve for p, what you would come up with is 0.75. It would just emerge from this analysis. If I set this binomial up this way and I said solve the equation for p, it would come out that p equals 0.75 because you saw 75 events out of 100. That is the value of p. It's the number you can put in p that would maximize this function. So you intuitively would say, oh yeah, it must be 70. The chances must be 0.75. But to mathematically prove it, you would actually fit a model to it. You would say, I saw 75 ones out of 100 total. And then you would solve this mathematically. This could be solved with calculus very easily. With more variables, it gets more complicated. But you would say that you would actually discover that this function is maximized when p is 0.75. It's the most likely value of the probability. You saw 75. So the chances, the most likely thing that in the population, the most likely thing is that it is actually 0.75. It could be 0.79. It could be 0.72, right? And that's where confidence intervals and hypothesis testing come in, right? You want to know, like, well, could I rule out that it's 0.65? Can I rule in that it is? You know, that you use these equations and the resulting betas and so forth to prove that. And so you need sort of this is the mathematical representation of your data. Logistic regression is using the binomial under the hood. And so here, this is actually, this little silly thing that we just did is exactly the same as fitting a really, it's the same as fitting a really dumb logistic regression model. Well, all there is an intercept. A no x variable model is what we just solved, actually. And if you fit a data set with just 75 ones and then 25 zeros and ran a logistic model on that, you would get this with the intercept 1.0986. And if you took the odds of, if you took the e to this, that would be the odds of disease for, that would be sort of essentially the odds of disease, and you get that to be equal to 3. And if you fit sort of our usual formula here, 1 plus e to the minus blah, 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 that's just the alpha, you get 0.75. Whoa, look at that. Logistic regression just gave you 0.75. This is just to prove to you that under the hood, it is actually fitting this formula, solving it, and reporting back to you what it found. And it found 1.0986, which if you throw into your formula, gives you that the probability of disease is equal to 0.75. This is the process. Now, it gets really, really complicated because underneath the hood here, it's actually going to be putting the full logistic model with all your alphas and your betas and all of that good stuff, and it's going to get much more complicated than a single parameter. And that's really where Zach's stuff takes over. But the idea here is that it's really modeling a lot of sort of simultaneous binomial distributions to your data. The reason we care about this for hypothesis testing right now is the likelihood, this quantity that represents these probability distributions, is sort of, it has a few properties that are really interesting. So for a given data set, let's say I have the same 290 cases of data from Grady. I fit the same model 3 times, or not, I fit 3 different models to the same data set. One has just x1 and x2, the other one is x1, x2, x3, and so forth. I keep adding stuff into the model to the same data set. Okay, if you do this, what happens is the likelihood, that quantity that sort of represents the probability of all your data and all, the probability distribution of all your data sort of keeps getting bigger. The more you throw in the model, this likelihood quantity sort of keeps increasing like this, so that the smallest likelihood is always from the model with the least stuff in it, and then as you add more stuff, the likelihood function increases. And there's this thing called the likelihood ratio test. And the likelihood ratio test sort of uses this relationship to its advantage. And the idea here is at some point, you start adding sort of meaningless things into the model. Like at some point, your model, like the 20th variable you added doesn't give you much more information over the other 19 that are already in your model. This sort of is the same intuition with the sums of squares tests that we do for linear regression. The more stuff at some point there's these diminishing returns. You keep throwing stuff in your model and you're not really getting much out of it. And since the logistic model works with likelihoods, it doesn't work with sums of squares, so we can't do a sums of squares test to see if sums of squares change when we add things to the model. The version that we do is the likelihood test. And the likelihood, this idea is the probability, the fit, the likelihood is a sense sort of a quantity of the fit, how good, how probable sort of all this information is. it sort of starts to increase less and less the more you put in the model. And so there's this task that we're going to develop that says, like, look, I just added another 2 factors to the model. Does the likelihood really significantly change? And this is exactly the same as do the sums of squares appreciably change when I add more stuff to my linear regression model. And basically, we make a test called the likelihood ratio test. And it actually doesn't use the likelihood directly. It uses this thing called the negative 2 times the log likelihood. This is actually what the computer outputs, but it's a function of the likelihood itself. And the idea here is that you can use this likelihood information that the model's developing all of its estimates on to your advantage to do a statistical test of whether 1 beta or 10 betas or however many betas you want to throw in the model are statistically significant, sort of when considered together. And so what you do is you take 2 models, one that has all the variables, the full model, and then the reduced model that drops any number of variables. I want to test 5 variables are not significant or whatever it is. You compare their likelihoods by really comparing the difference of the negative 2 log likelihoods. This here, it's the reduced minus the full. And the idea here is that this quantity is small if the differences between the 2 models is small. Like if you get no new added information out of the extra variables in the full model, this difference is not very big. And if it is really, really big, that means, wow, the full model has something going on. There's some sort of more information, explanatory power, as it were, in these extra covariates. And this is going to be a big quantity. And so the distribution, sort of where you define the cut point on how much is significant, is determined by the chi-square distribution. And so the chi-square, it's a chi-square distribution with the number of degrees of freedom associated with how many things you're dropping. So if I'm only looking at a model that's dropping 1 variable, then it's a 1 degree of freedom. If it's dropping 10, it's a 10 degree of freedom test. This is exactly like the F tests where in the last year when the degrees of freedom were determined also by the number of things you dropped. So it's exactly the same idea, but this is the logistic regression analog. And so here, imagine you have a model, you just want to test beta 3 equals 0 versus an alternative where it's not equal to 0, it's just very simple, sort of 2-sided, is it significant at all in any direction sort of test. You compare 2 models, one where, let's say here's a full model that has beta 3, whatever this is, let's say it's sex in the MRSA analysis or any variable. You compare this full model to a reduced model that's exactly the same but drops the thing you care about. So you sort of delete the thing that you're probing whether it matters, and you get out of SAS you're going to get the negative 2 log likelihood for one model, compare it to the other, and that is going to have a chi-square 1 degree of freedom test because you dropped one thing. Simple as that. So here, again, here's just an example. This is a situation where we're dropping 2 variables at a time. Here, this is testing. Here's a model that has interaction. Beta 5 and beta 6 represent these 2 interaction terms of x1, x3, and so forth. So here, a test that comparing this model to the model that has just x1 and x2 and x3 is a test of whether the null hypothesis is that they're both equal to 0 versus at least one of them is not 0. This is sort of that, again, this is it should be statistical tongue twisting that you should remember from before, where sort of you're saying at least one of them is not 0. It could be both could be significant, one could be significant, but they're both, it's not the null hypothesis where they both don't matter. It's sort of the idea. And that's sort of what these statistical tests are about. And this would be a 2 degree of freedom test. So one more thing just to keep in mind is that sometimes we're going to have categorical predictors with like 5 levels. You know, you're going to have, I used 4 cities before, let's say it's 5 counties or whatever, I don't know, I'm using geography, but it can be 5 levels of anything. That's going to be represented by 4 dummy variables in your analysis. So the test of county in that model is actually going to be this group test, a chunk test is what it was called in linear regression. It's going to be a test of 4 things. It's not going to be a 1 degree of freedom test because there's 4 dummy variables for 5 counties. It's a 4 degree of freedom test, and it's going to be done like this, sort of in a group way. So to test a bigger quantity of variables that associated with things you might put in a class statement that have more than one level, you're going to need to do the likelihood ratio test in order to do that. So there's another thing. There's another way to do this. There's something called the wall test. This is sort of the quick and easy test. This is when you sort of scan the value. This thing that we did before involves you actually running two models. You got to actually run the model one way and run it the other way and make a comparison. Two calls to proc logistic. The easy way is SAS is going to give you a column of p-values. Okay, those p-values are actually the wall test. They're not the likelihood ratio test. It's a slightly different test. They usually give you similar answers. And it's the column of stuff that you're going to get out of SAS are these 1 degree of freedom wall tests. And they're very similar to the t-tests that you saw before. And so, for example, if you wanted to just compare, and let's say this very simple model, it's a model with just beta 1, I mean, x1, x2, x3, 3 terms. And you just want to know, is beta 3 significant? That's it. I want to know that. Simple enough. One thing, I have a question about one variable. I'm not comparing two variables or anything crazy. Then the value of beta hat over the standard error of beta hat is normally distributed 0, 1 under the null hypothesis of whichever beta, beta 3 is equal to 0. Okay, so SAS is going to give you, I think, do we have it on the next slide? No, it's not up here. But remember, we saw that table of estimates where you have sort of that SAS in its output gives you the estimate and then the standard error of the estimate, and then it gives you a p-value next to it. That's all this wall test stuff. If you divide the estimate over its standard error in that table, you're going to get the test statistic and you can get the p-value. You don't actually need the whole table. You could just use the beta and the standard error and do the wall test manually yourself, because one over the other is a normal distributed thing. And so that's just that. It's a very sort of quick and easy test. This is very much the analog of the t-test that we did in linear regression. You get the same table in linear proc reg or GLM, and it's t-tests. Note that some packages in some places will do this as a chi-squared 1 degree of freedom test. And it's the square of this formula is distributed chi-square instead of z. So some places you might see this as a walled chi-square test. But it's really the same old thing. It's just the square of this formula, and it happens to be chi-square 1 distributed rather than normal distributed. But the basic idea is if you got a value of 1.96, right, if I have beta hat over standard error of beta hat, and I get 1.96, that's a borderline significant result. If you looked it up, it would be, right, that would be a p-value of 0.05. Remember, 1.96 is that sort of magic 95% normal distribution cut point. So if I did this ratio on my data, if SAS gives me an estimate and the standard error, and this thing is equal to 22, it's super duper significant. You don't even need a p-value. I'll tell you it's really significant because it's way bigger. It's way out on the normal distribution from 1.96. 22 is huge. You could say it's less than 0.001. You don't even need to do anything. So this, you can almost eyeball it, or if you have a value from this and you looked it up on a normal 0-1 table, you can sort of get the p-value. So this is a quicker and easier answer, in a sense, relative to the likelihood ratio test. And generally, they sort of give you the same answer. So I'll just jump to the end and sort of say that the likelihood ratio test is sort of the more powerful test. It tends to give you slightly smaller p-values. It's a little more of an efficient statistical procedure. And so it's sort of the preferred analysis. In common practice, it's a lot easier to sort of get quick answers out of the wall test. And the reason it's quick is because it's automatically in the output. You only have to run one model instead of running two models and then sort of doing the difference. Again, you should know how to do both. On exams, we would like you to know how to do both. But in practice, the likelihood ratio test is a little more annoying to do. The one bonus here is that the likelihood ratio test lets you test a lot of variables at one time. And so there's some situations where you're really going to want to do that, particularly if you want to test, like, is there any interaction on the model? And you want to test 10 things, all the interaction terms, or some big global assessments. The wall test is just a column of p-values for one factor at a time. And you can't just look at 10 p-values really and say, oh, none of, like these two and that one are not significant or whatever it is, because the model, they're all sort of conditional on the other. So this is this idea. I know I'm reviewing a lot of linear regression really quickly, so I'm sorry. So we're trying to get to the new stuff. But there's this thing about the type 3 versus type 1 tests. Do you remember that business in linear regression? Type 1 and type 3 sums of squares? No? No way. Okay, so then you learned it as the type 3 sums of squares. So that basically the idea is when you get a column of p-values from any of these statistical procedures, they're all sort of like, if I see p.01 for sex, it's actually for sex, that's the p-value for sex in a model that already has all the other stuff. And so if I took sex out of the model, all the other variables would change, all the other p-values would change. And so you can't sort of globally just sort of scan them and be like, those three are significant, and then take them out. Because it turns out if I remove sex, then something I thought maybe that wasn't significant might suddenly jump out and become significant. Because what if sex was highly related to another variable, and they were sort of accounting for each other in some way. And this is an issue we deal a lot with in linear regression. We have sort of two variables that sort of overlap, and one becomes significant when you take the other out of the model. That's sort of the problem with the walled tests, is that they're sort of all mutually controlling for everything else. And so you're not able to sort of test everything together by eyeballing a bunch of p-values that each are considering the other factors. And that's sort of the danger to the walled tests. Convenience, laziness, sort of makes us want to do the walled test, but the likelihood ratio lets you properly test the union of a bunch of things. So that's just sort of an overview of those, and we're going to use both of them throughout the class. So the last thing is the confidence intervals. The confidence interval really repeats a formula that, again, that we've seen from linear regression. And it's based on the walled statistics. So it's very, very similar to the walled tests from before. And if you wanted a confidence interval for beta 3, your estimate of beta 3, then its confidence interval is beta 3 hat, the estimate that you get out of SAS, plus or minus this sort of z statistic, where 1 minus alpha over 2 is the cut point, so that's 1.96. For a 95% interval, that's sort of the value we use, which is the value of the z distribution with 2.5% on either side, and times the standard error of beta 3. Okay, so this is sort of the confidence interval cousin of this. Right? They're super duper interrelated. This is the walled hypothesis test, and the walled confidence interval is the estimate plus or minus 1.96 times the standard error of the estimate. This has come up, I'm sure, in every class, even for stuff in the table-based analyses. This formula rears its head in the Mantel-Hansel procedures and so forth. This idea that it's the quantity plus or minus the standard error of the quantity. This is actually not for the confidence interval. So I try to put this part down here. This is the confidence interval for the odds ratio. This is the confidence interval for the beta, for the thing that's on the log odds scale. Remember that on the log odds scale, it's alpha plus beta 1 times x1, beta 2 times x2, and so forth. So this is the formula for the interval around the betas themselves. We actually don't care about the betas themselves, usually. We care about the e to the betas. Those are actually the odds ratio. Those are actually the things we care about. So we exponentiate them. And so the idea here is that e to the beta 3 plus or minus the same expression gives you an interval for the odds ratio. Right? So when you do it, in reality what you do is you do it the minus way, right? You do e to the beta 3 minus 1.96 times the standard error. That's the lower bound. And then the upper bound is the plus version, right? So e to the beta 3 plus the z statistic times standard error. So that's the idea. This is exactly a formula that you've seen for the risk ratio in stratified analysis, and now we're seeing it for the odds ratio in the logistic model. And if you want a different, percent confidence interval, right, so you can put in cut points that correspond to the 90% confidence interval and 99%. Most often we use the 95% confidence interval as a sort of a rule of thumb. This has to get modified a little bit if this formula is going to change as life gets more complicated. I'm just going to say that. And as actually it's going to come up on the next slide. It gets more complicated when you don't have a dichotomous exposure, not a 0-1. That's one thing. And it gets more complicated when there's interaction. Okay? And what basically happens is when there's interaction, let's say this is we just talked about earlier how if there's interaction with the exposure variable, the odds ratio has more things going on. It's not just beta 3, it's beta 3, it's beta 5, it's beta 6. Okay, times x, and you have times x1 and x2. So this is not so easy. Okay, this is a little bit more of a complex expression because it's not just e to this for the odds ratio, it's plus or minus 1.96 times the standard error or the square root of the variance of this whole thing. And the standard error of this whole thing is actually a really complex formula. It's not just the sums of the standard errors individually. It's actually based on a matrix of all of the pairwise relationships. And so this, don't do this at home, or do it at home, but with SAS is sort of the idea that this sort of gets to a level of computational complexity where you can't just take the output off the shelf and do it yourself. And so we're going to use the contrast statements in our homeworks and labs, and so in our estimate statements and so forth to do all that. This has to be done with either the contrast or the estimate statement to sort of request a complex odds ratio and its confidence interval. So just to sort of line these up, this is exactly what we said before, sort of what we did in linear regression and sort of what's the logistic analog. So this is sort of the cheat sheet on all the things we did. And if you line them up, you're like, oh yeah, of course, that's exactly what we used to call the chunk test. For the chunk F test is just the likelihood ratio test. Because we don't have sums of squares and mean squares anymore, we have likelihoods now. But it's sort of the same. You're seeing this all through a funhouse mirror. Now it's logistic regression, is the idea here. So that's the end of that slide set. We're going to switch to talking about the EVW model. Yes, thank you. Any questions before we sort of just slightly shift gears? This is a time, or you can just stretch. So that was like there's a lot of the statistical aspects of linear regression revisited quickly. The idea is that hopefully homework 0 got you a little more in the mode to be talking about these things. And we're going to go over this again in the labs. We're going to sort of keep drilling these ideas home. So, yes, question. Oh.
So, are you saying you can't use the wall test for categorical variables that aren't binary?
Sort of. Okay. Sort of. So the reason it's sort of is, depends how you put the binary variables into SAS. Okay, so if you made manually in a data step, like 4 dummy variables as yourself, you didn't use a class statement, then what you're going to get in the SAS output is 4 rows of, output for those dummy variables, each with a p-value, and you're not going to be able to say anything collectively, because you're not going to, testing any one by itself is sort of meaningless. You sort of need to collect them and test them together. If you use the class statement, it will actually give you a 4 degree of freedom wall test. So SAS has a way to again, it's an ugly formula. It's not just, the way it's doing it to get to the standard error is not so straightforward. But if you do a class statement, it will give you a joint wall test. So it depends how you do it. So by default, if you do your own dummy variables, you have to use the likelihood ratio. So in practice, in life, you're going to mostly use the class statement, hopefully. Otherwise, you're spending a lot of time making dummy variables. So in all of the regression procedures, the class statement says, hey SAS, this variable has 1, 2, 3, 4 doesn't actually mean 1, 2, 3, 4. Instead, it means categories. And so the class statement says, hey SAS, go make dummy variables. And when it does that, it actually switches the output to do a multiple degree of freedom wall test. It does. Still, the likelihood ratio is going to be the smaller of the p-values. In practice, the open secret is you're probably going to use a wall test because it's the thing that you're given fastest. And they're often going to be very similar. Any other questions? Thank you. So the EVW model, this is something a little different. So this is, we're going to sort of spend the next few weeks using a different nomenclature for our logistic regression models. And this is sort of gone over a lot in the book, this system, because this is a Dr. K sort of innovation or something that he's sort of developed, this sort of way of thinking about around modeling. And the idea here is this thing called the EVW model is a system, as it says here, for naming and organizing predictors and their coefficients in the model. And the basic idea is that, you know, you have in epi life and research, not every X variable is the same. Some are exposures, some are confounders, some are effect modifiers, some are mediators, which we don't talk as much in this course, but I'd love to on the side. But you know, there's other things that not all X variables are created equal, and they do different things. And if you have a logistic model with 15 beta times X's, you're going to sort of intuitively start treating the variables very similarly, even though you shouldn't analytically. The exposure variables and their outputs, the estimates and the standard errors, actually should be interpreted sort of differently and used sort of differently than the confounder variables. We actually don't care about the confounders usually in the model. We're trying to adjust for them. We're sort of trying to get rid of them in some sense. We want to sort of focus on the exposure. We did the study to learn about the exposure. We don't care about the control variable, the confounders. And we also sort of, in our formulas, we don't want to necessarily treat the two equally. So my disclaimer is this is a really useful system that I encourage, but this is really sort of an optional way to sort of view, it's a different way to view the logistic model. Everything's mathematically the same as just calling everything beta times X, and like most statistical textbooks would, but this is a way to think about it specifically for epi research. This is like an epidemiologist's way to view the logistic model. Okay, so that's all this is. We're just going to sort of turn things on its head a little bit and see the model a little differently. And we're going to sort of think about 4 different types of variables. E, C's, and they're in parentheses for reasons I'll explain, the V's and W's. So at first you're going to be like, why are you making me learn all these extra letters? This is very annoying. So that's okay. It's a healthy initial reaction. And then I hope over time you're going to be like, oh, I get it. That was really convenient. So it might take you like a week. You're going to first be annoyed. Why are we doing this? And then you're going to be like, okay, that actually was really convenient. Because what happens is that this lets us represent epi concepts very quickly with our model in a way that if we had a sea of betas and X's, it's sort of this thing you have to cut through that's very irritating. And the idea here is in our study, we measure 2 things as sort of our primary things, right? We have exposures, the reasons we're doing the study. We're trying to quantify this environmental toxin, and we want to see that sexual exposure, whether it occurred or whatever the things that we think about as sort of the why we did the study. And then there's the control variables, the everything else that we measure along the way because it's potentially a confounder. You'd look really foolish if you didn't ask that on your questionnaire. There's always these things that we do because there's other ancillary things that we got to keep track of in our study because we may want to deal with them in our analysis. Right, and those are the control variables. And those are in C's. These C's are going to pop up in the variable and then formulas at first, and then we're going to switch to V's and W's. The V's and the W's are something else. They're derivative from the C's, okay? And they're essentially confounders and effect modifiers, okay? Sometimes a control variable that we measure is only potentially a confounder, and sometimes it may also be an effect modifier. These are sort of designations for what a control variable means in our analysis. And I'll show this sort of by example because it's a little weird. But the idea here is that a control variable can feature as either a confounder or an effect modifier. And depending on what it's doing in the model, we're going to call this, we may call the same variable a V or a W, depending on what its sort of theorized purpose is. But we only measure 2 things in the study, the exposure and the controls. And we also measure the disease outcome, but we know that already. So that's sort of the jumping off point. So we're going to jump back into this MRSA example. You're probably tired of it. I'm sorry. But it's sort of convenient to keep revisiting and layering on more stuff on the same example. So here we saw, this is just the stratified analysis from before. So here is a really simple model. This is the crude model, the unadjusted model. It's alpha plus beta 1 times previous hospitalization, but now I'm going to call it E. Okay, so the exposure, I don't care what it is, we're just going to call it E. Okay, and then where E is actually this thing called previous hospitalization. We're not going to call it X, we're not going to call it pre-hosp, we're just going to call it E. Okay, and you need to know that E equals previous hospitalization. Okay, so again, here's sort of what the results look like for that. Here's the odds ratio, 11.67. So this is the simplest EVW model. It's a model that has only an E, where E is previous hospitalization. It's got no V's, it's got no W's, it's got nothing else. It's got an intercept, but they all have intercepts. So this is the simplest EVW model where only the exposure is included. That's it. Super uninteresting. But the idea is we're no longer calling this X or pre-hosp or whatever we want to call it. Okay, let's take a model. Let's think about age, sex, and PAMU. Here's sort of a different model. This is not exactly that one because this is a no interaction model, but here's a model that has one exposure and 3 C variables. Okay, where C is C2. Oh, this is supposed to. These are off. Oh no, something happened. Oh no, I swear. Okay, this should be. We're gonna do whatever. We're gonna change this. It's not letting me change it. Okay, pretend these are 1, 2, 3 or similar, and that these sort of correspond to them. These should sort of line up here, or 2, 3, 4. The basic idea is you have 3 C variables, each with their own coefficient, betas. Okay, in this situation, the C, we can call whichever one. This C is age, sex, and PAMU. I'm sorry, these numbers don't line up, and these are the same numbers. So I'm going to say that not only is this a model that had an E and 3 C's, but it not only was that, there was 3 control variables. Here, this is 1, 2, 3. That looks better. Not only was this a model with an exposure, previous hospitalization, but it had 3 control variables. Okay? Whoa, sorry. 3 control variables, age, sex, PAMU, okay? There are 3 control variables, and there are also these V1, 2, and 3. We're going to call them actually V1, 2, and 3. Why are we doing this? The reason is that these are confounder control variables. There's no interactions. They're not effect modifiers. When there are, we're going to call them W's. In this model, there are 3 things we controlled for, and by the way, there's also 3 confounding sort of control variables, these that we're going to call V. Okay? So that's just a thing to know. There's 3 V's, 3 C's, and an exposure. And by the way, these are sort of the same. Again, you're probably still in the why is he doing this phase. So we're going to emerge from the why is he doing this phase. Okay, here's another model. Okay, a little more complicated. Now there's interaction. Okay, so we got this other thing, and now the 1, 2, 3 is fixed. Yay. We have 1 exposure, 3 C control variables, age, sex, and PAMU. So 4 things were measured in this study, essentially. Okay? But there's 7 terms in the model. Okay? So the C's are getting recycled. They're getting used multiple times, okay? As is the exposure. We're sort of recycling things. So now there's more terms than stuff we measured. And lo and behold, age appears in 2 sort of roles. Hats, role. You shouldn't say hats because it has a statistical meaning, so wardrobes. And age appears in 2 ways, okay? It's both a control variable for the sake of confounding up in here, and it also reappears down here as a product multiplying exposure. And since it's multiplying exposure, it's an effect modifier, right? That's sort of like, by definition, like that's what it means. Remember, it's the odds ratio, like back 45 minutes ago, the odds ratio changed when we had something multiplying by the exposure. It's an effect modifier. Right? E times C1 means C1 is modifying the effect of the exposure in sort of in our odds ratios. So what we're going to say here is age plays 2 roles. It is involved as V1 and is also involved as W1. Okay? Same with sex, same with PAMU. Each one in this specific model appears twice. They don't have to appear twice. In this model, they sort of appear twice. The same C is both a confounder and an effect modifier. So the idea here is we're starting to sort of label what each term in the model is doing. Some terms are confounding only sort of consideration and some are effect modifier consideration. And that's going to be really helpful in sort of dealing with the analysis. Okay, so here's a really crazier model. Here's a crazier model. This one might be irritating. Here, not only do we have sort of the main effects, here we have another thing, C1 squared. Why would we do that? Well, C1 is age, and age is continuous. Maybe age squared is meaningful in the analysis, right? In linear regression, I'm sure you had some examples where there were sort of quadratic terms or sort of complex, you know, or I don't know, cubic terms or things like that that represented something that's beyond sort of linear effects of a continuous, in the continuous data of your linear model. Here you might say, well, maybe for some reason, because of some a priori interest, particularly in, I'm thinking of like toxicology studies where you may have very complex nonlinear relationships, you may have a squared term. Okay, and then here we have not just interaction, here's an interaction term between two C's, but not involving the exposure. Here, there's a whole bunch of things involving the exposure, and this one is three terms, there's a three-way interaction, exposure with two C's. These are all very, very different according to the EVW nomenclature. Okay, so let's like take this apart. Why? This is annoying, but possibly realistic. Okay, and so we have to come up with a way to epidemiologically break this out. C1 squared is a function of C1. It's C1 times C1. Okay, that's actually another V term. So we said before that age, sex, and PAMU were sort of confounder terms. Age squared is the same thing. It's another term that you'd be controlling for. It has nothing to do with exposure. If you did your odds ratio formula, it's going to cancel out. It doesn't involve exposure. It is going to cancel out. It's a funky confounding variable, but it's one nonetheless. It's just age times age. And because it doesn't involve exposure, it's just going to wind up being a confounder sort of adjustment term. You're adjusting for age squared, just like it was something else. And so the fact that it's squared doesn't really matter. It's actually functioning as a fourth confounder sort of variable in the model. The same goes for C2 times C3. So this also involves no exposure. And again, in your odds ratio formula, it's going to cancel out when you're thinking about the odds ratio for exposure. And it happens to also be an interaction term, but it's a different kind of interaction term than effect modification. All right, effect modification is the specific interaction between your exposure and something else. And so this is an interaction term, but for the sake of caring about confounders, we're going to treat it in the modeling strategy part, particularly that's coming up next week, we're going to treat it as if it's just another confounder. It happens to be a variable that's derived from others, but we're going to treat it as a fifth confounder. The fifth confounder happens to be a product of two other confounders. Or potential confounders, because we may decide they're not confounders, you know, after we sort of go through the analysis and start dropping things. So these are funky, but they're still confounders because they don't involve the exposure. Then take the next few terms. Here's this one, E times C1. That is actually an effect modifier term that involves age, and that's W1. This is just E times W1 it would be sort of another way of representing this, this first term here. These are all W's because they are all interaction terms that involve the exposure. This thing has a three-way interaction. I still don't care. I'm just going to call it W4. And W4 is another effect modifier formed by the product of sex and PAMU. Okay, so this is just a way to sort of rewrite things in terms of what's an exposure, what's a confounder, what's an effect modifier. And it takes something really complex and it's going to make it actually less complex. So here's what we're going to do. Here was the original model we just talked about. C1 squared, C2, C3, you know, and so forth. Okay. We defined V1, 2, 3, 4, and then W1, 2, 3, 4, and then V5. Sorry, this was the V5. We are going to replace all of these sort of primary variables with their V and W equivalents, like this. Bam, done. Okay, so these C's, even C1 squared, just get replaced by V1 through 4. And I don't care what is inside of W, 1, 2, 3, 4, but we're going to swap them out and sort of replace them like this. And E times C1, or E times C1 becomes E times W1, which is age. And E times W4 is E times C2 times C3, okay? So now I made your life more complicated. We used to have like just betas and x's, and now we got a whole lot going on. But what got easier is you don't have to keep track of what is inside of these as directly. So V4 happens to be C1 squared, W4 happens to be C2, C3. We're going to sort of not keep track of those for a little bit. We're going to free ourselves up from all of what's going on inside of there. And just these terms are confounders, these are effect modifiers. And notice we also changed all the betas into other Greek letters, make life more fun. These gammas represent the coefficients for the confounder terms, and the deltas represent the beta, what we used to call betas, for the effect modifiers. This is going to be a different notation system for us, but it's exactly the same as lots of betas and x's. SAS doesn't know, SAS doesn't care, it just gives you stuff, right? No one actually has to know other than us. This is our epi secret. This is our way of sort of handling the notation in an epi-friendly way that's going to let us sort of assess confounding, assess effect modification in a very systematic way. Bless you. So here's sort of formally everything we just said. That we could sort of, these are sort of the definitions of all these things, right? So disease and exposure, I don't need to tell you about that. Covariates that we want to control for as either confounders or effect modifiers, and they sort of star as V's or W's in the model. They sort of, that's sort of where they show up. Right, that the potential confounders may be C's, like C's naked all alone, or is C squared, or C2 times C3, or whatever it is. Does not involve the exposure. And then the W's are the potential effect modifiers that are also C's, or functions of C's. And they don't involve you don't include the exposure in defining them, but they're always multiplied times the E. They're always multiplied times their exposure. So here, E times W4 means E times C2, C3. Okay, so I'm just gonna, so are we at time? Both clocks are off, which is mind-boggling. We are at time. They're both behind. So, so I'm just going to leave you with this, that we're going to rewrite the logistic model in terms of this new notation, and it's going to make writing odds ratios easier, and it's going to make assessing confounding easier. It's going to make life easier after it gets harder. So it's going to be great. Not to sound like any presidential candidates. This is going to be better than that.